Okay, so we left off last time. We had essentially finished up the LU decomposition. Any questions outstanding from last time? Okay, so I didn't write up all of the details of the factorizations like I had last time, but just to remind us of what we're working through. So we talked about the LU. We'll talk in a bit of detail about the Cholesky today, but you'll be focusing more on that in the problem set. And then we'll talk in a fair amount of detail about the QR decomposition today as well, which is used a lot for regression type calculations. And then on Wednesday, I'll hit some of the highlights of Eigen decompositions and singular value decompositions without going into a lot of the computational details. So that's basically the plan for the rest of this unit on linear algebra. Okay, so for the Cholesky decomposition, the idea is this is relevant when we have a positive definite, or we'll see that it can also be used for positive semi-definite matrices. And so by definition of having something positive definite, we have something symmetric, and that's going to make our job easier. I already said last time that we're going to have half as many calculations as with the LU, and that sort of makes sense intuitively because we only have half as many unique elements of the resulting A matrix that we're interested in since it's symmetric. Okay, so the idea is we're going to try and compute, so we're going to have this decomposition, some upper triangular matrix U times its transpose times itself. And the actual the basic Cholesky factorization is not very hard to come up with. We just sort of write it out like this, and then we start working through what are the individual values of the U matrix have to be. So I'm just going to look at the upper triangle of A, since the lower triangle I can just get as the transpose of the upper triangle. And so the basic steps are, well, okay, what's A11? Well, in this factorization, it's just going to be this column, which mostly has zeros, times this row, which mostly has zeros. So I'm just going to get that U11 squared is equal to A11. So I can get U11 as the square root of A11. And for the purpose of getting a unique Cholesky decomposition, this is defined to be the positive square root. Okay, so that's going to give us this guy. And now the idea is we're going to proceed this way and fill in the elements of, we're going to sort of proceed this way, and that's going to allow us to fill in to figure out what the required elements of the U matrix are. Okay, so to compute A12, what would we do? Well, we would take the second column times the first row. So again, that's going to be an easy calculation. The only relevant things here are going to be U12 times U11. Okay, so we're going to have U12, U11 equals A12, and we can then solve for U12 as A12 over U11, and of course we've already computed U11, so we know what that guy is. And I should be able to proceed in similar fashion along this row, and I'll just get that U1j is A1j over U11. Okay, so that's going to allow me to finish off and figure out that row of the U matrix. Okay, questions or comments at this point? Okay, so then we can then proceed to the next one. We're not going to bother with this because we've already figured out what A12 is. So we need to know what A22 is. So that's going to be the second column times the second row. We're going to get U12 squared plus U22 squared equals A22. We already know what U12 is. We're just going to solve for U22. That's going to involve another square root. And we're going to get that. And then similarly, as we proceed down, we're going to end up with Uij being this equation here, which is not hard to work out. It's just a matter of the bookkeeping of the elements of the matrices. So in some sense, that's sort of all there is to the Cholesky decomposition. There's nothing particularly hard about it as long as we sort of proceed in this organized fashion to figure out what the elements are. And on the homework, you'll sort of work through this, and you'll have to work through the details to figure out how many calculations are involved in doing this. And you presumably will not be surprised to see that this is going to end up being order of n cubed, and you'll work out exactly what the order is. Again, if we sort of look at this from a sort of airplane's altitude perspective on this, we're going to see that this is basically 3 nested for loops, and that's consistent with this idea that we've got an n cubed calculation here. Okay, so if we think about then, okay, so we've got this U transpose U decomposition. What do we do with it? What is it useful for? Right? So one thing we can do is we can actually solve systems of equations. If we wanted to solve the system of equation that has solution A inverse B equals X, well, I can write A as U transpose U. I can then write U transpose U inverse as the inverse of the individual elements, having to transpose them. So the usual rules about dealing with transposes. So we've got U transpose U inverse. That's going to be U inverse times U transpose inverse. And so that's where I've got this from. And then a couple things to look at here. Now that we've sort of looked through these things a little bit, you should be able to say off the top of your head, okay, how many calculations are there involved there? Well, we have to get the Cholesky decomposition. That's order of n cubed, right? Then we have to do these calculations here, but what is this? We've already seen this. What is this calculation? Okay, so it's order n squared, and what have we called that calculation? What have we named it as? So U transpose is lower triangular, so that's a forward solve, right? So that's n squared, and then U inverse times the result of that is going to be a back solve. Right? So we've got a Cholesky decomposition, a forward solve, and a back solve. We know that one of those is n cubed, and 2 of those are n squared, so that gives us some idea of what the calculations are. And we also know that we definitely don't want to do this first and then multiply by b. Okay, so in R, this is easy to do. This is, once we've got U, which is just, U is just Cholesky of A, we can call the back solve to do a forward, we can call the back solve function to do a forward solve because we've got it. The Cholesky decomposition by default gives us back the upper triangular factor. And so we just say transpose equals true in order to use the upper triangular factor, but to be able to actually do the forward solve. Okay, any questions about that? Yeah, that's a good question. I haven't actually looked that up. My understanding is it's a bit more expensive than a multiplication, but it's not too bad. And as you'll work through it, I think what you should see is that there are only n of them. And so therefore, as n increases, the amount of calculation involved in the square root relative to the multiplications becomes negligible. Yeah. And actually, that's a good lead into this other comment I have here in the notes, which is there is a way to do a Cholesky decomposition that doesn't involve calculating square roots. The other thing I'll mention here, I forget if I may have said this before, although maybe we concentrate on the Eigen decomposition for generating random normals. But if I take x equals U transpose times z for z being standard normal, that's going to give me back covariance of x equals a. So this is another recipe for generating multivariate random normals. And another thing that this brings up that we can think about here is, okay, U transpose is a lower triangular matrix. We're multiplying it by a vector of z's. So again, this idea of thinking about basis vectors and partitioning variability, by doing the Cholesky decomposition, we can think about we can interpret that as we've decomposed this into a set of n basis vectors. And to generate a random multivariate normal from that, we're going to take a basis coefficient, just standard normal, multiply it by the first column. That's the first component of variation. Z2 times the second column is the second component of variation, and so on and so forth. So again, we're sort of building up variation, building up random vectors with components of variation. Questions? Yeah, yeah.
You already have mentioned this, but why all the diagonal elements of the A are all positive?
And just by construction here, that we can take in each case we're taking a square root to get the diagonal elements.
I'm talking about the original matrix A.
Oh, the original matrix A, right. That is a positive definite matrix, so the diagonal elements are the variances, so they have to be bigger than 0. Okay, so we could actually do least squares with a Cholesky decomposition. We could take the Cholesky decomposition of x transpose x and then do the system, solving the system of equations x transpose x inverse times x transpose y. Turns out the standard approach to do that is not to use Cholesky, but to use the QR decomposition for reasons that we'll see in a few minutes. Okay, then the last thing I want to mention is that we can have numerical issues with the Cholesky decomposition, or for that matter, with the Eigen decomposition with positive definite matrices. So I forget we might have done this a similar example before. But here's an example. This is again going back to this idea of generating a Gaussian process that represents a time series over a discrete set of times. So this matrix C that I'm going to generate should be, mathematically speaking, it should be a covariance matrix. It should be positive definite. It should have all positive eigenvalues, and I should be able to take its Cholesky decomposition by the algorithm that I laid out here, or by alternative algorithms. But if I do the Eigen decomposition of E and I look at the eigenvalues, what I see is that some of the ones that are ordered last here, the smallest magnitude eigenvalues, actually have negative values. Okay, so this means the matrix, even though it is mathematically positive definite, is not numerically positive definite for the sorts of numerical precision reasons that we've now seen in a few different contexts. And more to the point here in terms of the Cholesky decomposition, if we try and do this Cholesky decomposition, it fails. It says the leading minor of order 37. I don't remember exactly off the top of my head exactly what that means. I think that might have to do with the upper 37 by 37 matrix, but I'd have to look into that to remind myself what that is. But it's basically saying, wait a minute, you gave me I was expecting a positive definite matrix. I tried to work my way through the calculations, and I got to a point at which I was not able to do the calculation, which indicated it to me, the computer, it seems like it's not positive definite. And if we go back to the notes, we can see where things might go awry, which is here we've got a UII that we're calculating as a square root of something minus something. This is a sum of positive values, so that's going to be positive. This AI is also positive for the reasons that we were just discussing. But it could be possible that we could get a negative value when we subtract these two numbers. And the case is that will not happen in mathematical terms with a positive definite matrix. But if we have imprecision, and we do in doing our calculations and in representing the numbers, then we could numerically get that this is a negative number. The algorithm then tries to take a square root of the negative number, and presumably what happens is that error message is in response to trying to take the square root of a negative number, or an analogous kind of calculation in the other ways of doing the Cholesky decomposition. Okay, so that basically happens when the matrix is very ill-conditioned, when we've got that the ratio of the largest magnitude and smallest magnitude eigenvalues is very, very large, which is the basic context in which we've seen that there are going to be problems. In this example here, if I went back to R, what I would see is that the condition number of this matrix is something like 10 to the 18th. Okay, so again, getting to be larger than the precision with which we can, the number of digits that we can represent numbers accurately. And there's have a little bit of logic here about sort of what can go wrong, which is, well, I'll let you guys read that on your own time. But it's basically the sort of reasoning that we've seen in other contexts. The nice thing is that we can actually get around this numerically, and that is basically a similar solution to what we did with the LU decomposition of exchanging rows, of pivoting. So if instead, in R instead I say pivot equals true for this same matrix C that just failed when I tried to do the decomposition, it'll return U. It'll give me a warning message that says there's a problem with this rank, with the rank of this matrix, and analogously that it seems like it's not positive definite. And if I look at U, let's look at the lower portion of U, the lower right corner of U. Basically what happens is that it ends up putting, let's see, is there a good way to show this? Let's see, so this is, okay, so we would expect with the usual Cholesky decomposition that we're going to get values that are not zero on the diagonal and on the upper triangle. Is it a 1? All right, so I'm a little bit stumped because what I'm about to tell you in terms of what pivoting does with the Cholesky decomposition is that it puts a whole bunch of zeros in that lower corner. So I'm a little bit surprised to see that it actually has a 1 here in the 100 comma 100 element. So I'm not sure what's going on with that. I'll have to defer that and see if I can figure out what's going on with that offline. Be that as it may, the basic story when we do the Cholesky decomposition with pivoting is as follows. We basically, where are my notes here? The basic idea is instead of creating the original U, we're going to create U transpose U that equals some PA for orthogonal P, just like with the LU decomposition. We're going to do some reordering of either rows or columns of the matrix. And the result of having done that is we're going to get a U that, another way of looking at it is we're going to get a U matrix where we basically zero out this piece of the matrix. And what we've done in doing so, what we should be able to do is, if we go back to what the decomposition is, as we're moving along here, the first thing we do when we get to a row is we try and calculate UII. And so we could, for example, see that this is going to give us a negative value. And we can basically replace that. Oh, okay. Now I'm sort of remembering what's going on with this. We can basically replace that UII with a 0, and we can replace the. I think we're going to replace the entire row with a 0. So that is going to. That's going to sort of deal with this numerical issue. So I'm wondering if sort of that's, the other thing I was going to say is you could basically reorder the rows. If you see this happening, you could shift this row down and then shift another row up. That's what I was saying with the P matrix there. And you could sort of choose optimally which row to shift up to give you the largest value of this difference here. That's going to stabilize the calculation. So if you did do the shifting and move the ones where you got the negative values down, you can create a Cholesky factor that looks like this. And if we now go back and think about the U transpose Z generating random normals according to this, based on this factorization, this matrix, when I transpose it, is going to look like this. I'm multiplying by Z's here. So what am I doing? Again, going back to the idea of having basis factors, I'm creating these basis factors, but then I'm saying, well, I don't actually need n basis factors to represent the variation in this particular problem. I'm going to zero some of them out because these columns are basically redundant with these other columns. And so basically whichever z's correspond to these are not going to get used because they're just going to get multiplied by zeros. So I'm basically using a lower dimensional representation to create my multivariate random normal vector. Okay, so that's that's sort of the basic idea of what happens with numerical issues in the Cholesky decomposition, is we basically end up zeroing things out when we see these negative, when they see these values that are negative, where we would be needing to take a square root. Okay, and that's sort of similar to the pseudo-inverse that we talked about of putting in, instead of putting in 1 over 0 equals infinity or an eigenvalue, when we try and take the inverse of the diagonal matrix of eigenvalues, we put in a 0. So again, it's this idea of sort of zeroing out some of the components of the decomposition. Okay, so any questions about that? Okay, so let's move on and talk about the QR decomposition. So the basic idea is we're going to decompose some matrix X, which can be a rectangular matrix, and in fact that's sort of the canonical example, is we're decomposing an X a design matrix or predictor matrix for a regression problem. So we're going to decompose it into an orthogonal matrix and an upper triangular matrix. Okay, so we have some matrix. I'm going to make it n by p, and I'm going to make it look like n is bigger than p to be in sort of to have it evoke the regression context for us. And we're going to decompose that into some n by n matrix. That's going to be our Q matrix, and that's going to be orthogonal. And then an n by p matrix that is going to be our upper triangular matrix. So this matrix is going to look like this. It's going to have zeros down here. And it's also going to have zeros down in the lower rows as well. So the result is, a standard way of writing this decomposition is not to write out the zeros here or the columns that correspond to these rows, since they're just going to get zeroed out when we multiply by this block of rows. But we're just going to write out what's called the skinny QR, which is this is just going to be p orthogonal columns. And we're just going to look at this upper triangular, at this piece, which contains the full upper triangular matrix. So that's going to be this sort of standard, at least in our context, that's going to be the standard QR, is this submatrix of Q in this submatrix of R. Okay, so why is it useful to come up with this? Well, one is that if we look at X transpose X and think about the fact that that's going to come up in regression a lot, well, that's just R transpose, that's just transposing QR, which gives us R transpose Q transpose. This is an orthogonal matrix, so the Q transpose Q disappears, and we just get R transpose R. And we're then going to be able to use that to do, we're going to be able to use these things to do regression. So you'll notice that this is basically giving us the Cholesky factor of the X transpose X matrix. Okay. So if we skip ahead for a second and think about what happens when we do regression, well, we're trying to solve this system of equations. We've got this matrix multiplied by the beta that we're looking for, and that's getting, and then the result of doing that matrix vector multiplication is X transpose Y. So we're trying to find X transpose X inverse X transpose Y. If we write it out like this and start replacing the X's with the QR factorization, well, we get this on this side. Again, the Q transpose Q disappears. That's just the identity. We get R transpose Q here. R transpose is invertible, so we can just pre-multiply each side of the equation by R transpose inverse. And we get it down to just R beta equals Q transpose Y. Well, if we've done our factorization in QR, all that's left to do in terms of finding beta is just to, this is now an upper triangular matrix, is just to do a back solve. And we just go ahead and do a back solve, and we've got beta. And it also turns out that once you've got the R matrix and the Q matrix, there are some very elegant results that sort of fall out when you sort of play through thinking about using R and Q to figure out what are the residuals, what are the sum of square errors, what's the hat matrix, all of the quantities that come about in regression. It turns out you can write down really easily and compute really easily once you've got Q and once you've got the Q and the R matrices from the QR decomposition. Okay, so they're basically, well, I guess I'm sort of skipping around here in a way that's maybe not particularly helpful. Let me say this first. So one reason for doing the QR decomposition is that if you think about numerical accuracy in this context, the condition number of x transpose x is basically the square of the condition number of x. So QR allows us to do the factorization on x, and that gives us a condition number that is the square root of if we did the factorization on x transpose x. So that's a benefit in doing the QR on x, and then doing the sort of calculations that I just indicated that are disappearing off the screen, as opposed to explicitly multiplying x transpose x and then doing something like the Cholesky decomposition. So there are numerical reasons for doing that. The thing I do want to mention at this point is if we think about what's the context in which x transpose x is not going to be very well behaved and x transpose x is going to have a large condition number, the context where that's going to happen is when we have columns of the x matrix that are nearly collinear. So that's generally a situation in statistics that we want to try and avoid and like orthogonalize the columns or use some other strategy for dealing with that. It's also the case where if you look at the variances of the beta hats and the covariances of the beta hats that correspond to the collinear columns of x, you're going to have really, really high variances and covariances because you don't know whether it's this column or that column that's explaining the variation in the response. So we could spend a lot of time trying to come up with better numerical estimates of what exactly the betas are, but in some sense from a statistical perspective there's not a lot of gain from doing that because the statistical uncertainty in those beta hats is very large. So I can come up with a very, much more accurate estimate of what beta hat 6 is, but if the variance of beta hat 6 is very, very large, maybe I don't care that I'm getting a very, very precise estimate of the point estimator. So in some ways, sort of thinking on numerical precision is is from a statistical perspective, maybe a bit of a side issue here. But in any event, that's sort of one of the reasons that people tend to use the QR decomposition to solve the least squares problem. Okay, so it turns out that if we were using QR to factorize a square matrix, it would require 2n cubed over 3 calculations, which is more than either the LU or the Cholesky decomposition. So this is not a great approach if we're trying to deal with a regular full square matrix. If instead we're doing least squares and we're working with x transpose x, which is going to be p by p, then we can work through how many calculations are involved in taking x and either computing x transpose x or taking x and doing the QR decomposition and then doing the least squares problem, the least squares solution. And what you would see is that basically for the Cholesky, it's this term with n's and p's in it. There's another thing called sweeping that looks like this. The householder method for QR, which we're going to see in a second, is this. This is another approach to doing QR. So it's sort of, as you sort of look at what are the terms, what are the constants in front of the np squared and in front of the p cubed, each of these, well, I guess it sort of depends on which one we look at. Each of these has an np squared, and then some of them have a p cubed. But they've got different constants in front of them, and in some cases we're subtracting off the p cubed, and in some cases we're adding on some constant times the p cubed. So depending on the balance between how big is n relative to how big is p, you might choose which of these approaches you do differently because of the fact that things are going to trade off differently depending on how big those are. And if n is much bigger than p, then you could see if you sort of play around with this that that the Cholesky decomposition would actually turn out to be a better approach, just from the perspective of how many computations we have to do. Okay, so if we did our regression in R, it actually uses the QR decomposition, and it uses this QR function, which calls a Fortran function from the linear algebra package, LAPACK, behind the scenes. And basically, if you look at the result of using the QR function in R, what it's basically returning is a single matrix, and on the upper triangle is the R factor, and the lower triangle is numbers that tell you how to do the that basically give you information about how Q is constructed, in particular using the Householder transformation approach that we're going to talk about in a second. So if you really want to, if you then want to multiply something by Q or multiply it by Q transpose, you use these various methods that are associated with an object in the QR class. So this goes back to S3 R object-oriented stuff. And if you really want to extract out the actual Q matrix and the actual R matrix, there are also R methods that will extract that out of the of X, which is going to be of the QR class. Or X.QR is going to be of the QR class, sorry. Okay, so questions before I launch into computation? Okay, so the basic idea when we're thinking about doing this QR decomposition is I'm basically trying to come up with an R by doing transformations that can be represented as multiplying by an orthogonal matrix. And basically I'm going to be trying to take my original X matrix and basically inject zeros into the matrix. And there are a few different ways that I can go about injecting zeros such that I replace the X matrix with a matrix that looks like that. So the first approach is something called householder reflections. And the basic idea is as follows. So we'll just sort of do this in 2 dimensions in the simple case to start off with. So suppose I have some vector x here. And now I suppose I have basis vectors u and v that span this 2-dimensional space. So suppose this is u and this, or suppose this is u and this is v, that I've got this set of basically of axes for the space. Then what I can do is I can basically reflect x across v, and which we can also think of as reflecting x sort of in the u direction. And if I reflect x, I'm going to get an x that looks like this. And so it turns out that the way I can do this reflection is I can do this reflection by taking q times x, and the way that I come up with q to reflect along the direction u is that the Q matrix is constructed as being I minus 2 u transpose for a basis vector u that tells us about this direction here. So that will basically do this reflection here. And this matrix is orthogonal here. And so what's the trick that we're trying to do to zero out elements of the X matrix? Well, one way we can think of this is, suppose I have my vector x. I want to do a reflection that's going to put this vector on the axis here. Okay, and the result of that is if this vector is represented as x1, x2, those are the coordinates that define this point, I'm going to reflect it and I'm going to get it to be here. And the nice thing about this is going to be some x1 tilde 0, and I've zeroed out one of the parts of this vector. So the idea is that I'm going to choose my u and my v such that this is going to be, sorry, I'm not drawing very well here. This is going to be v here, and this is going to be u here. And if I choose this to be u, I'm reflecting across v, I'm reflecting in the direction of u. That's going to reflect this vector to be here. And that's going to zero out this component of the vector. And you can do this in higher dimensions as well as in 2 dimensions. So the idea is to do it in this way. Then what I need to do is I need to take u, so this is going to be my new vector x tilde that I'm trying to come up with. So I can take u as x minus x tilde over the norm of x minus x tilde. And if I wrote out q times x, so if I take this u, I construct this q, and I multiply that q times x, I would see that the result that I get is indeed this x tilde. You could work through the details if you wanted to do that. Okay, so that's a householder reflection. So how is this useful in terms of thinking about the QR decomposition? Well, the idea is I want to start with my my X matrix. Did I call it X here? Hopefully I did. Okay. And I'm going to do some Q1 transformation that does a householder reflection. And the goal of that is to produce a new matrix that is again, there's sort of a lot of the difficulty here is just doing the bookkeeping. So what is this supposed to do? This Q1 is supposed to take the first column of X and use a cleverly chosen reflection such that it's going to reflect in such a way that I basically zero out all of the remaining components of this first column of X. And if I do that, you can see I'm partway towards creating my decomposition X equals QR, because the point is I want to get an R matrix that in the first column is zeroed out such that I can start to construct it such that I'm getting an R that's an upper triangular matrix. And I know this Q matrix is orthogonal because that's how these reflection matrices are orthogonal. So once I do that, that's the first step in creating this matrix. And now what I'm going to do is I'm going to choose another cleverly chosen Q2 that's going to zero out all of the all but the first 2 elements of the second column. So the idea is I'm going to erase this here. If I now think about this matrix here, what my Q2 needs to be is it needs to be 1 and then a set of zeros. That's basically, if you sort of work through the details, that's going to keep everything here as it is after we've done the first reflection. And now this is going to be, what am I using for my notation here? I'm going to call this Q2 1 to indicate I'm doing this sort of iterative procedure. So this is going to be the full Q2, and the idea is once I've gotten it down to this problem, I'm now going to take a submatrix Q2-1 that is basically going to do the same thing to this submatrix that I did to the original matrix. So I'm going to have Q2 of 1 times this X1 matrix, and that's going to give me, I guess my notation here is now X21, the length of that, and then zeros, and I'm going to call this thing R2, just whatever the result is in that first row of having applied these transformations. And then I'm going to get down here, I'm going to get some X2 matrix. So now I have, if I now think of putting this matrix back in here, I've achieved what I need for the first column and what I need for the second column. I'm just going to proceed with this submatrix. I'm going to come up with some Q3, Q4, Q5, etc. And I'm just going to march my way down and basically zero out the pieces that I need to zero out. So as a result of having done this, I'm going to end up with QP minus 1 multiplied all the way down to Q1 times X. The result of that is going to give me my upper triangular matrix R. And if I want to figure out what the Q matrix that results from multiplying all these orthogonal matrices together, that's still going to give me an orthogonal matrix. So I can just take the transpose of this, that's the inverse, and that's going to give me the actual Q matrix. By multiplying this by here, that's going to give me the identity here, and by pre-multiplying by R, I'm going to have Q times R is equal to X. So that's the basic idea of the householder approach to doing the QR. Okay, questions about that? Okay, so the second approach that sometimes gets used is called the Givens rotation approach to getting the QR. It's somewhat similar in this idea of we're sort of manipulating the columns of this matrix X to basically zero out pieces of that matrix and get to the R matrix. In this case, we were doing these reflections, but another way to get X to be on the axis and therefore to zero out a component of the vector is to rotate it instead of reflecting it. So the idea of the Givens approach is we're going to cleverly do clever rotations to basically rotate the columns of the X matrix. Okay, so we're going to go back to a little bit of, again, back to some high school math and think about trigonometry. So, that's not what I wanted to do. Okay, so if I think about again, I'm going to start in 2 dimensions for the sake of simplicity. And I think about this vector x1, x2. If I want to zero out x2, what I can do is I can rotate this matrix, this vector, to be on the axis. So this is some theta. If I rotate it, I'm going to get some new vector that is that I'm going to call x tilde. And one way so basically what I'm going to do is I'm going to try and take x1, x2. I'm going to try to take this vector and make it my new x tilde, which is going to be the length of x and then 0. So that's the rotation I'm doing. That's what I'm trying to achieve. And I can do this with an orthogonal matrix Q, which is just the cosine of theta, that theta is the angle there, times the sine of theta minus sine of theta, cosine of theta. So this is a little rotation matrix. What it does is it rotates by theta. If I had a minus here, it would rotate in the counterclockwise direction as opposed to the clockwise direction. And another way to write this, if we think about the trigonometry of cosines and the hypotenuse and the adjacent and the opposite and all that business, is that Q is equal to x1 from here over the length of x. And this is x2 over the length of x. This is minus x2. So this is another way of expressing this matrix Q, just in terms of the components of my original x vector. Okay, so that's in 2 dimensions. That's pretty straightforward. You can also show that if we're working in a large dimensional space, we can basically rotate in 2 out of say the p dimensions of the space. So we can isolate to a 2-dimensional subspace and rotate in that subspace. And if we did that, for example, suppose I have x is equal to x1, xp, xq. I guess I'm thinking of n as being the length here. The way that I rotate in the 2-dimensional subspace corresponding to p and q here is pretty straightforward. I basically make the Q matrix that I'm going to call Q sub PQ of theta. And basically what that matrix is it's a diagonal matrix, except, it's more or less a diagonal matrix, except in the PQ positions. So here are the 4 elements that are in sort of the PQ column and row positions here. So these 4 elements are basically going to be these 4 elements here, but substituted into this larger diagonal matrix. So that's going to rotate in this subspace. And so if I do that, if I take a matrix that looks like this and has, depending on how we represent it, has these 4 values or these 4 values in these places in that matrix, then what happens is I'm basically going to take this vector, everything except for these 2 elements are going to remain the same. This is going to become it's basically going to become this xp tilde, and this is going to become 0. So I basically achieved the same thing in this 2-dimensional subspace that I was achieving here. Okay, so that's sort of this idea of doing Givens rotations, and the idea in terms of of how that applies for the QR decomposition is. Think about my X matrix. I'm going to apply some Q12 that does this rotation in the 1-2 dimensions to X, and that's going to zero out this position, the 1-2 position. Okay. Then I'm going to work in the 1-3 subspace. I'm going to do a rotation there that's going to zero out the 3rd position. So I'm going to zero out this guy here. The result of this is this value keeps changing as I do these successive rotations. Okay. But I'm basically going to work my way all the way through, doing Q1n up through Q12, such that I zero out all of these elements of the first column. So that's the first step. Well, that's one step that's composed of multiple steps. And then I'm going to proceed in similar fashion with the second column and the remaining columns to zero things out. So Q22 is then going to, actually maybe my notation is bad because I presumably have this and this, so I presumably want to call that Q23 instead of Q22. So I'm trying to zero out this guy by doing the rotation in the 2-3 subspace, and then 2-4, and then so on and so forth. So I basically work my way down and zero out those guys, and then I just continue in this fashion. Each of these matrix Q, if you look into these, look into the details of these matrices, is also orthogonal, and so the result of having accumulated all of these Qs is going to be that this is orthogonal as well. I've already gotten my R by having zeroed out all of the pieces, elements of Q. And then if I explicitly want to know what Q is, well, again, just like with the Householder approach, I can just take the transpose of this and multiply it by this to basically get back X here and get the X in front of, to get the Q in front of the R matrix there. Okay, so that's the approach that uses rotations to get the QR. And yeah, why don't we quit there? I'll go quickly over the third approach to doing a QR, which is Graham-Schmidt orthogonalization, which is something you've probably seen in linear algebra. And then we'll talk about the Eigen decomposition, the SVD, and some computational stuff in R next time.